everyone. My name is Clarissa Rincon, and my mentor for this research project is Dr. Yihan. And I collaborated with Pablo Delgado as well on the research regarding the assessment of upper limb task and joint-based exoskeletons for rehabilitation. Next slide, please. As a background, a traditional rehabilitation setting would include a physical therapist driving a motion while the patient remains passive. Now, this method could result in loss of interest from the patient as well as high costs. Therefore, exoskeletons and other robotic devices have been introduced into rehabilitation area to automate rehabilitation exercises. Now, this new method has developed several benefits, such as since the patient is actively involved during the motions, this results in more rapid and effective recoveries from the patient, as well as the exoskeletons are able to take the physical load off of the physical therapist, which results in more intensive training period. Next slide, please. Now, although the exoskeletons have developed several benefits into the rehabilitation areas, there are still some challenges that exoskeleton developers face. And one of them, and the most common, is misalignment. Misalignment occurs when the exoskeleton does not properly align to the user's body, which could lead to serious injuries. And it typically happens when the exoskeleton is designed in a way that it mimics and simplifies the human body. And this creates an issue because the human body is composed of complex joints that cannot be mechanically replicated. Therefore, this research seeks to assess two types of exoskeleton designs on their alignment at the elbow joint, while the elbow flexion and extension motion is simulated using the OpenSim software. Next slide, please. The first design assessed is the joint-based exoskeleton design, and this design focuses more on mimicking the human body and its joints. And it is a 5 degree of freedom mechanism composed of 5 links and a stand. And as shown in the image to the right, links 1, 4, 5, and the stand are adjustable for height variability as well as anthropometric variability between users. And the overall exoskeleton is composed of 5 joints that can generate different rehabilitation motion tests, such as shoulder flexion extension, shoulder adduction abduction, shoulder elevation depression, and elbow flexion and extension. And overall, 5 motors are the ones that drive the exoskeleton to perform these different rehabilitation tests. Next slide, please. The next design is the task-based exoskeleton design, and this design focuses more on generating a specific task without specifically mimicking the human body and its joints. And it is a 1 degree of freedom parallel mechanism that is composed of 4 links and is driven by a single motor. And this exoskeleton can only generate one rehabilitation motion, which is the elbow flexion and extension. Next slide, please. Now, there are several research objectives that I focused on throughout the research project, and one of them being is quantifying the misalignment present in a joint-based and task-based exoskeleton design while the elbow flexion and extension motion is simulated, as well as quantifying the misalignment's effects on the muscle tendons of the main flexor and extensor muscles, identifying a safe range of motion of the elbow flexion and extension motion that avoids high levels of misalignment that could lead to serious injuries for each exoskeleton, and finally identifying a preferred exoskeleton design based on the results. Next slide, please. For the assessment, there were several steps that needed to be followed and are chronologically listed. The first one being modeling both exoskeletons within an existing musculoskeletal model, as well as simulating the elbow flexion and extension motion within OpenSim, and quantifying the misalignment by determining the position displacement between the human elbow joint and its respective exoskeleton joints, and examining the variation in muscle tendon lengths when the identified misalignments are simulated. Next slide, please. So like I mentioned, the first step in the assessment process is modeling both exoskeletons within an existing musculoskeletal model. And OpenSim is able to offer several different musculoskeletal models. However, the upper extremity dynamic model was chosen for this research project because the upper body is replicated more properly and is most similar to the actual human body's function. Therefore, that model was used for this research project. And as you can see, the image to the left is the joint-based exoskeleton with the musculoskeletal model, and the image to the right demonstrates the task-based exoskeleton with the musculoskeletal model as well. Next slide, please. The next step was actually simulating the elbow flexion and extension motion within OpenSim, and the motion was able to be simulated using previously recorded motion capture data. So the trajectory obtained was converted into motion using the inverse kinematics toolbox within OpenSim and a predetermined marker set. So the motion was simulated from 44 degrees to 126 degrees approximately. And as shown on the image to the top right is the musculoskeletal model with the joint-based exoskeleton performing elbow flexion, and right below it is it performing elbow extension. Next slide, please. In order to begin the actual quantification of the misalignment of each exoskeleton at the elbow joint, the body kinematics toolbox within OpenSim was used since it provided information about the ulna's position as well as its respective exoskeleton parts position throughout the generated motion. And so the position vectors of both parts were compared, and the maximum displacements in the X, Y, and Z axis were identified and used to develop a new human model where its ulna was displaced with the maximum displacement values. Next slide, please. Now, as you can see in this slide, to the left is the joint-based exoskeleton misalignment throughout the elbow flexion and extension motion in the X, Y, and Z direction, as well as to the right is the task-based exoskeleton misalignment throughout the same generated motion. And right below it is the table containing the maximum displacement values for the joint-based and task-based exoskeleton in the X, Y, and Z axes. Next slide, please. Now, the next step after quantifying the misalignments present for each exoskeleton design is actually identifying and quantifying the effects that it had on the muscle tendon length for the flexor and extensor muscles observed. And typically, a muscle tendon can elongate 10% of its initial length prior to becoming damaged. Therefore, these 10% values were calculated for the muscles observed, and the results demonstrated that 4 out of the 8 muscles exceeded their elongation limit, and these 4 muscles includes the brachialis, the triceps medial, the triceps lateral, and the anconeus. As you can see to the right is an example of the results found for the brachialis, the top one being for the joint base, and as you can see, the maximum variation in the results is approximately 1.3 millimeters, whereas the task-based brachialis demonstrated a maximum variation of approximately 0.9 millimeters, whereas the brachialis 10% elongation limit is approximately 0.4 millimeters. So as you can see, the limit was highly exceeded, and this could lead to injuries over time. Next slide, please. Therefore, further procedures were performed to identify a safe range of motion of the elbow flexion and extension motion that all the muscles could successfully satisfy their elongation limits. And it was found that all muscle tendons observed satisfied their elongation limits when the motion was generated from 44 degrees to 70 degrees and 44 degrees to 100 degrees for the joint-based and task-based exoskeletons, respectively. And as you can see right below is the example of the brachialis results for the joint-based and task-based exoskeletons. As you can see for the joint-based exoskeleton, the maximum variation was approximately 0.3 millimeters. And similarly, the task-based exoskeleton brachialis demonstrated a maximum variation of approximately 0.3 millimeters, while as you recall, the 10% elongation limit of the Brachialis is approximately 0.4 millimeters. Therefore, um, um, limiting the range of motion to these angles demonstrated to have the muscle tendons successfully satisfy their elongation limit. Next slide, please. So to conclude, this study presented the assessment of a joint-based and test-based exoskeleton for upper limb rehabilitation under alignment to the human elbow joint using the OpenSim software. The results demonstrated that the muscle tendon lengths observed exceeded their elongation limit when the motion was generated from 44 degrees to 126 degrees, which could result in serious injuries with long-term use. It was later found that a smaller motion range of 44 degrees to 70 degrees and 44 degrees to 100 degrees satisfies the elongation limit of all muscles for the joint-based and task-based exoskeletons respectively. So based on the results, although both exoskeletons demonstrated a misalignment, it can be concluded that the task-based exoskeleton performed better than the joint-based exoskeleton during the assessment at the elbow joint. Next slide, please. And these are the references used in order to compose this PowerPoint slide. And I am open now for questions. So this assessment method is to be used during the design process of an exoskeleton. Therefore, an exoskeleton developer could use this assessment in order to already improve its design during the design process rather than already having a prototype. However, this assessment method could also be used when the exoskeleton is also already developed, which, like I did my research project, limiting the range of motion in order to target the safe range of motion in which the misalignment is not, there's not high levels of misalignment that could lead to serious injuries. So I believe that the best option would be to either modify the design in order to satisfy the alignment. So based on the results, using those results in order to make those adjustments, or limiting the range of motion of the generated motion or rehabilitation task that could target that safe range. So my current research focused more on the assessment at the elbow joint. However, the joint-based exoskeleton is able to create motion from the shoulder. So I would like to continue performing this assessment on the joint-based exoskeleton with the shoulder-based motions rehabilitation task. So to conclude, yes, I would like to continue this research and hopefully incorporate it in a long-term project.